The requirement in 310.4 regarding parallel conductors being the same length is intended to ensure that each parallel conductor carries its fair share of the current. Parallel conductors are used to increase ampacity for a circuit where a single conductor would be insufficient. When conductors are run in parallel, it's critical that they have similar characteristics, specifically impedance, so that the current divides equally among them. Unequal impedance can lead to one conductor carrying more current than the others, causing it to overheat and potentially create a fire hazard. A 2-foot difference in length on a 50-foot run represents a 4% difference. The key concern with unequal lengths is the potential for unequal impedance. Impedance is the total opposition to current flow in an alternating current circuit and includes resistance, inductive reactance, and capacitive reactance. A difference in length will primarily affect the inductive reactance of the conductors. Inductive reactance is directly proportional to the length of the conductor and the frequency of the alternating current. Even a small difference in inductive reactance can cause a significant imbalance in current distribution, especially at higher current levels. If the impedance of the parallel conductors is not balanced, circulating currents can develop. Circulating currents flow between the parallel conductors themselves, rather than through the load. These currents can cause additional heating in the conductors, further exacerbating the problem of unequal current distribution. In the described situation, several factors influence whether a 2-foot difference in a 50-foot run is problematic. Firstly, the conductor size and material need consideration. Larger conductors have lower resistance, making them less susceptible to impedance imbalances caused by minor length differences. Copper conductors have lower resistance than aluminum conductors, so the same length difference will have a smaller impact on copper conductors. Secondly, the current level in the circuit must be known. At lower current levels, a small impedance imbalance may not cause significant overheating. However, at higher current levels, even a small imbalance can lead to dangerous temperature increases. Thirdly, the frequency of the alternating current needs consideration. Higher frequencies will exacerbate the effects of inductive reactance, making the length difference more significant. Fourthly, the spacing between the conductors must be known. Conductors that are close together will have higher mutual inductance, which can help to balance the impedance. The conduit material, whether metallic or non-metallic, also has an effect on inductance. Metallic conduits can reduce inductance due to eddy current losses in the conduit itself. Fifthly, the type of load connected to the circuit must be known. Nonlinear loads, such as those found in electronic equipment, can generate harmonics that can exacerbate the effects of impedance imbalances. There are several practical steps you can take to mitigate the effects of unequal conductor lengths. Firstly, ensure that the conductors are bundled together as closely as possible. This will increase mutual inductance and help to balance the impedance. Secondly, use metallic conduit where possible. Metallic conduit will reduce inductance and help to dissipate heat. Thirdly, consider using larger conductors than required by code. Larger conductors will have lower resistance and be less susceptible to impedance imbalances. Fourthly, vary the ampacity of the circuit to account for the potential for unequal current distribution. This will reduce the overall current level and minimize the risk of overheating. Fifthly, use an ammeter to measure the current in each parallel conductor under full load conditions. If the currents are significantly different, take steps to correct the imbalance. If it is truly impractical to equalize the lengths, there are alternative conductor arrangements that can be considered. Firstly, twisted pairs can be used. In a twisted pair arrangement, the conductors are twisted together, which helps to balance the inductance and reduce circulating currents. Secondly, shielded cables can be used. Shielded cables have a metallic shield that surrounds the conductors, which helps to reduce electromagnetic interference and balance the impedance. The inspector's concern is valid, as the code intends for parallel conductors to share current equally. However, a rigid interpretation of the same length requirement may not always be practical or necessary. Providing the inspector with a detailed analysis of the situation, including calculations of impedance and current distribution, can help to demonstrate that the 2-foot difference in length does not pose a significant safety hazard. Calculations can be made to estimate the actual impedance difference and the resulting current imbalance. Software tools and online calculators are available to assist with these calculations. An argument can be made that the increased labor and material costs of completely equalizing the lengths outweigh the minimal safety benefit. The inspector has the final say in whether or not to approve the installation. However, by providing the inspector with sufficient information and demonstrating a thorough understanding of the underlying principles, it may be possible to obtain approval for the installation as is. Regarding specific requirements within the National Electrical Code, or NEC, several sections are relevant to parallel conductors. 310.10 H covers the general requirements for conductors in parallel. It specifies that conductors must be the same length, conductor material, circular mil area, insulation type, and be terminated in the same manner. 310.10 H2 addresses the paralleling of conductors in sizes 1/0 and larger. It emphasizes that all conductors must have the same electrical characteristics. Table 310.16 provides the allowable ampacities of insulated conductors rated up to 600 volts, which is essential for determining the appropriate conductor size for the intended load. 300.3 B1 covers the requirement that all conductors of the same circuit, including the grounded conductor and equipment grounding conductor, must be installed in the same raceway or cable. This requirement helps to minimize impedance and ensure proper operation of overcurrent protective devices. Article 250 covers grounding and bonding requirements. Proper grounding and bonding are essential for safety and to minimize the risk of electric shock. 250.122 specifies the minimum size of equipment grounding conductors, which must be sized according to the overcurrent protective device protecting the circuit. Article 314 covers outlet boxes, conduit bodies, and handhole enclosures. These enclosures must be sized appropriately to accommodate the conductors and splices without overcrowding. It is important to note that the NEC is a minimum standard, and local jurisdictions may have additional requirements. Always consult with the local electrical inspector to ensure compliance with all applicable codes and regulations. Using engineering judgment is also crucial. While the NEC provides specific rules, it also recognizes that there are situations where strict adherence to the rules may not be practical or necessary. In these cases, it is up to the engineer to use their knowledge and experience to make informed decisions that ensure the safety and reliability of the electrical system. The concept of impedance in alternating current circuits is fundamental to understanding the behavior of parallel conductors. Impedance is the total opposition to current flow and is measured in ohms. It consists of three components. Firstly, resistance, which is the opposition to current flow due to the material of the conductor. Secondly, inductive reactance, which is the opposition to current flow due to the inductance of the conductor. Thirdly, capacitive reactance, which is the opposition to current flow due to the capacitance of the conductor. In parallel conductors, the inductive reactance is the most significant factor affecting impedance balance. Inductive reactance is directly proportional to the frequency of the alternating current and the inductance of the conductor. The inductance of a conductor is determined by its length, diameter, and spacing from other conductors. To minimize impedance imbalances, it is important to keep the length of the parallel conductors as close as possible, bundle them together tightly, and use metallic conduit where possible. Grounding and bonding play a crucial role in ensuring the safety of electrical systems with parallel conductors. Grounding provides a path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same potential, minimizing the risk of electric shock. In systems with parallel conductors, it is especially important to ensure that the grounding and bonding are properly installed. The equipment grounding conductor must be sized according to the overcurrent protective device protecting the circuit. All metallic enclosures, such as conduit and junction boxes, must be bonded together. In addition to the code requirements, There are several best practices that can be followed to ensure the reliable operation of electrical systems with parallel conductors. Firstly, use high-quality conductors and connectors. High-quality components will minimize resistance and ensure a good electrical connection. Secondly, carefully plan the layout of the conductors to minimize length differences and ensure proper spacing. Thirdly, use a torque wrench to tighten all connections to the manufacturer's specifications. This will ensure a secure connection and prevent overheating. Fourthly, perform regular maintenance on the electrical system. This includes inspecting connections for corrosion, tightening loose connections, and testing the grounding system. If unequal lengths are unavoidable, consider adjusting the conductor size to compensate for the difference in impedance. For example, if one conductor is slightly shorter than the others, it may be possible to reduce its size slightly to increase its resistance and balance the impedance. This approach should be used with caution and only after careful calculations to ensure that the conductor is still adequately sized for the load. Another option is to use impedance matching devices, such as reactors or transformers, to balance the impedance of the parallel conductors. These devices can be used to add inductance or capacitance to one or more of the conductors to compensate for the length difference. However, impedance matching devices can be expensive and complex to install, so they should only be used as a last resort. Documentation is essential. Keep detailed records of the installation, including conductor lengths, sizes, materials, and connection details. These records will be helpful for troubleshooting any problems that may arise in the future. Regular inspections should be performed. Periodically inspect the installation for signs of overheating, corrosion, or loose connections. Any problems should be corrected promptly to prevent further damage or safety hazards. In summary, the NEC requires parallel conductors to be the same length to ensure equal current distribution and prevent overheating. While a 2-foot difference in a 50-foot run may not always be a significant safety hazard, it is important to carefully evaluate the situation and take steps to mitigate any potential risks. By following the code requirements, using good engineering judgment, and implementing best practices, it is possible to safely and reliably install electrical systems with parallel conductors. If the inspector remains unconvinced, consider involving a qualified electrical engineer to perform a detailed analysis of the installation and provide a written report. The engineer can assess the potential risks and recommend appropriate mitigation measures. The engineer can also serve as an expert witness if necessary. Open communication and a willingness to compromise are essential for resolving disputes with electrical inspectors. By working together, it is possible to find a solution that meets the requirements of the code and ensures the safety of the electrical system. Remember that the primary goal of the NEC is to protect people and property from electrical hazards. While strict adherence to the code is important, it is also important to use common sense and good engineering judgment to make informed decisions that ensure the safety and reliability of electrical systems. The specific application and the environment in which the parallel conductors are installed can also influence the acceptable length difference. For example, in corrosive environments, it is important to use corrosion-resistant materials and ensure that all connections are properly sealed. In high-temperature environments, it is important to use conductors with a high temperature rating and direct the ampacity accordingly. In hazardous locations, it is important to follow all applicable requirements for explosion-proof wiring. The 2-foot difference in length represents a small percentage of the overall run. The actual impedance difference may be negligible, especially if the conductors are properly sized and installed. Documenting the installation thoroughly, performing regular inspections, and being willing to work with the electrical inspector are all essential for ensuring the safe and reliable operation of electrical systems with parallel conductors. The length of the conductors is only one factor to consider when evaluating the safety and reliability of an electrical system. Other factors, such as conductor size, insulation type, and installation practices, are also important. By taking a holistic approach to electrical safety, it is possible to minimize the risk of electrical hazards and ensure the well-being of people and property.